we need to keep the idea of the anti-relationship of our leaving group and beta hydrogen in the E2 reaction in mind. But let's go back and look at an E2 reaction that I'm sure you've seen probably many, many times. Cyclohexyl bromide. Let's treat this with sodium hydroxide. And probably without thinking too much, you'd say, oh yeah, we got a strong base, we got a halide, it's secondary, it's a little bit hindered. We are going to do an E2 reaction. To do the E2 reaction, we need some beta hydrogens. We have them. In fact, we have plenty of them. We have some on this carbon as well. But I'm going to focus on these lower ones. And we'll go ahead and do an E2 reaction. And we will form our alkene. Great. Very simple question. You've seen it before. Now, let's try to keep in mind this idea that we need the anti-relationship between the beta hydrogen and the halide. So let's draw this starting material as a cyclohexane, because we need to keep in mind what's the relative orientation of all these groups. We would expect the bromide to prefer to be in the equatorial position. I'm going to fill in these key beta hydrogens. And now if we look at this, there is not a beta hydrogen that is anti to our leaving group, our halide. If we were to draw a Newman projection, what we'd see is this bond is actually anti to that CC bond. Well, that's not what we're going to attack with our base. So the fact is, this conformation of this molecule would not be very reactive for an E2. Well, darn, because this looks like a pretty good reaction. So how can we explain that this reaction does actually work? Well, remember, our chairs are in equilibrium. We can flip this chair. When we do that, this is an equatorial down bromide. And now when we flip it, it's going to still be down, but it's going to be axial down. And these beta hydrogens are also going to change their positions. And now when we do this, we see, this bromine, what is that bond anti to? It's anti to that hydrogen. So these axial groups are more able to undergo this elimination because they're anti to each other. So now our hydroxide can attack the beta hydrogen, that bond breaks, and it can kick at our halide, and we can meet this anti-requirement for this reaction. So looking at these reactions and realizing things have to be anti is not always as simple as when we draw these molecules in these flat representations. We need to consider what is the conformation of these molecules and how does this work. And we'll see how this can get actually a little bit more complicated in the next video.